Good morning. So, we are starting the lecture number 34. Before there was a break for about 10-12 days, I wish to recapitulate some of the materials which I covered in the last lecture. In lecture 33, that means the previous lecture, we started with drift diffusion model. In fact, all the derivations of current voltage relationship made prior to lecture number 33 did not consider the diffusion component of carrier flow. Only the drift component of carriers was considered. But actually speaking, the MOSFET otherwise is very similar to a bipolar junction transistor. So the carriers injected from the source and forming the inversion layer, they will move by the field induced by the drain voltage, and also partly due to the diffusion of carriers from the source towards the drain, because the source end will be higher, will have higher concentration of electrons in the inversion layer compared to the drain end. Therefore, there will be diffusion. Therefore, for a more accurate description of the current in a MOSFET, we should also consider the diffusion component. And in this particular lecture, I indicated that the current density, drain current density, has two parts. One is a drift component, the other is a diffusion component. This second component was not considered earlier than lecture number 33. Before that, we did not consider. Here we gave certain indications. I told you that JD, combining these two terms, can be expressed in terms of the Fermi potential gradient called electron Imrev gradient. This is the potential gradient, EY is the potential gradient, and this is the Fermi potential gradient. And taking this into consideration, and starting with that Qn equation, the inversion charge density equation, we wrote it like this, which is easy to understand. Nx is the electron density, volume density of electrons in the inversion layer, and we assume that it is distributed from the surface x is equal to 0 means surface to a point where the layer becomes intrinsic. That depth I called xi. Okay, so I integrate nx dx from 0 to xi and multiplied by q, and we get the number of inversion charge, the amount of charge in the inversion layer per unit surface area. Converting the integration from the space to potential, we use this equation. So we divide it by d psi dx, the denominator. We put d psi dx in the denominator, and in this numerator d psi. After cancellation, you see that it becomes the same. So because we had an expression for d psi dx, which we derived earlier, substituting that here, we really are making a transformation from integration over space, over distance, to integration over psi, over potential. This d psi was dropped in the last term, last equation. So d psi should be included. So this is how we can find an expression, more accurate expression for Qn, which is the charge density in the inversion layer per unit area, performing an integration over potential, not over distance. Then we write for ID, total drain current, in terms of JD, the drain current density, which is a function of x and y, assuming that the Z is very large, the depth is very large, and multiplied by W and dx. W dx is a slit area. The slit area of across the cross section, and integrating it from 0 to xi means over the entire cross section of the channel. That's how we get ID And we transform this ID equation like this, substituting for the current density and the electron then number nx dx, which is indicated here. You just see the equation derived earlier. So this is Qn nx dx. So nxy, substituting that here, it becomes like this. It becomes a double integral over x and y. X is perpendicular to the surface, that is perpendicular to the channel, and y is along the channel. Along the channel integration is from 0 to L, and perpendicular to the channel integration is from the surface to a depth I, xi. Substituting for the expression for, that this earlier things, nxy, which we did earlier, the qn that is, it is related to that, we get an equation like this, where this phi, that this, it becomes an integration. Instead of writing d phi n, we have written d phi here, indicating that this is a surface potential variation along the channel, along the length of the channel. And ID becomes now a double integral over potential from source end to the drain end, and over the potential normal to the channel from the surface, from the depth xi, which is where the potential is phi f, the intrinsic, and to the surface where the potential is the surface potential psi s. This double integral can be evaluated by, it not possible, but here it is possible to integrate it by analytically, it is possible. But if it is difficult, you can always do it by numerical technique. It's a very simple thing. And ultimately, this psi s has to be transformed from, ultimately the after integration you will get psi s. All psi will be replaced by psi s, and v will be replaced by vd. And we must know how vg is related to psi s, and we use a standard equation how vg is related to psi s. And using that, you can compute ID for different values of voltage, drain bias, and you can go for the entire range. There is no need of stopping somewhere, which was the case earlier. Up to that we computed, then we assume it to be saturation region. But here you can calculate it over the entire range. And as indicated earlier, these results, these theoretical results agree with the experimental results more properly, more precisely for long channel device, of course. This is purely a long channel device derivation. And people have shown that these curves are more closer to the experimental data for long channel MOSFETs. We also consider the subthreshold conduction, which I told becomes very important in the case of modern devices, where power consumption is an important criterion. So, because we have to minimize power consumption, sometimes we are tempted to drive the devices in a subthreshold design where the current is very small. So we need an expression to be derived. Of course, this derivation is for long channel device, and if you know the derivation for long channel, you can also attempt to make certain modifications for short channel, which is most important today. So you remember what I did, that I said that when Vg is less than Vt and is more than Vi, Vi means the voltage at which the surface becomes intrinsic. That means psi s is equal to phi f. For psi s lying between phi f and twice phi f, the surface will have some appreciable number of electrons, may not be very high. Above, when psi s exceeds to up to phi f, or when Vg exceeds Vt, the channel becomes strongly inverted. However, Below that and up to phi f for psi s and up to bi for Vg, the channel becomes very weakly inverted. That is why this region is called the region of weak inversion. Okay? And for that, we made a simplistic derivation of the current assuming a BJT model. We assumed that under this condition, because the electric field, the current flow is so small, the potential drop over the channel can be neglected. So the electric field along the channel, the tangential, that means the lateral component of electric field, or the along the channel component of electric field, EY, can be neglected, and hence we can consider only the diffusion component. And for that, we linearize the concentration gradient. Instead of writing dN dy, for simplicity, for analytical simplicity only, we write dN dy at n0 minus nL by L, writing n0 and nL using the Boltzmann approximation equations. And xi, here we assumed for derivation that the inversion layer is mostly confined not to a depth of xi, because it is perfect inversion layer. We say that it is the layer thickness at which the potential drops by VTH. You just see, this is a surface potential. The potential gradually decreases to 0, the substrate potential, okay? But then it decreases by VTH at a certain depth called Xi, and which we were defined as the inversion channel length, channel thickness. And that's why, and you see that we got this equation where Xi is given by VTH by this thing. VTH is nothing. What is VTH? VTH is the thermal voltage, not threshold voltage, thermal voltage, KT by Q, and this is the field at the surface. Okay, and field at the surface is given by this equation. The area of the channel is W into Xi. Area of the inversion layer channel is W into Xi, and Xi is given by this, and ultimately substituting them in the current equation, you get an equation like this, which is the current equation in the subthreshold region, in a weak inversion design. We expressed it in terms of the drain bias, the thermal voltage, and a parameter A, which was defined earlier and is given by epsilon s epsilon root 2 epsilon s by epsilon I into di by ld. And we noted that id becomes proportional to 1 minus e to the power vd by vth. It is proportional to e to the power psi s by vth, and is also proportional, and hence it is also proportional to roughly e to the power vg dashed by vth. So far as dependence of id on vg or psi s, it is exponential. It should increase exponentially with psi s or vg, and it should gradually, 1 minus vd, is very less dependent on vd because of this kind of nature of dependence. Because this term with positive vd, this term gradually becomes very small and negligible compared to unity. So the dependence on vd is extremely weak. Based on this, as I told in the last class, we get a curve, a plot of id versus vg for different values of vd, and we can also include vbs if you like, modifying the threshold voltage equation, and we get curve something like this. This is a logarithm of id versus vg. You note that this is almost a straight line. This is almost a straight line for low voltages, relatively low values of Vg, but beyond that it deviates from the linear relationship. However, the dependence on VD is very small, as indicated here. Dependence on VD is very small. As you go to the second year green curve, it is for a certain drain PBS, the substrate bias. You remember, I discussed about some dynamic definition of the threshold voltage. Threshold voltage normally in electrostatically is defined as a voltage for which the surface potential is twice phi f plus maybe some VTH, some 2 VTH or 3 VTH or 6 VTH, different definitions. But normally we assume that it is the value of VG. Threshold voltage is the value of the gate voltage for which the surface potential is twice phi f. That is the called electrostatic definition. In practice, when you make a device, and if you are interested in determining, calculating, finding the value of the VTH, it is better to plot ID versus VG and see where the threshold is occurring. At which value of gate voltage, suddenly the current rises from 0 to certain value, called threshold. But actually speaking, when you plot in the log scale, not a linear scale, it is a very sharp rise, but logarithmic rise, that means exponential increase. And we normally what we do, we usually draw a horizontal line through 10⁻⁶ at 1 microampere or 0.1 microampere or 0.01 microampere, depending on the kind of how small the device is. Usually for a macro device, typical long channel MOSFET, 1 microampere is a typical voltage which is used for defining the threshold voltage. So it is a cutting point of this line, which is 1 microampere, with this ID versus VG, that is more or less a measure of the threshold voltage. So this is the threshold voltage. You see that here the threshold voltage is practically independent of VD, and that is well known because drain bias will practically have no effect on the threshold voltage for an ordinary long channel device. Whereas as you go to short channel, you will find these two curves become appreciably separated for two voltages. For a short channel device, when you plot a similar curve, you will find these two curves become appreciably separated, as indicated. It is not indicated, it is for long channel device. Okay? And also if you repeat the experiment with the drain substrate bias, this curve moves to the right, and that is what is expected. You know, the body effect or substrate bias effect increases or enhances the value of the threshold voltage. That is clearly indicated here. Then, what was desirable for such variation is that this slope of these curves should be as high as possible. If I define the slope as this tan theta, of course normally this slope is defined as inverse of that, S inverse, which I did not mention in the last class. Somebody mentioned after class, I remember, that yes, this slope, this subthreshold slope S is the inverse of tan theta. Inverse of tan theta, okay, reciprocal of tan theta. And we define it in a manner which is as follows. Subthreshold slope is another very, very important parameter of a MOSFET, just like threshold voltage, which is the gate voltage swing needed to change ID by a decade. So here, if the current changes from 10⁻⁸ to 10⁻⁹, or 10⁻⁹ to 10⁻⁸, 10⁻⁸ to 10⁻⁷, by 1 decade, what is the corresponding swing, corresponding change in the threshold voltage? So it is a reciprocal of this slope. If you define the slope like this tan theta, then our definition of S is nothing but the inverse of tan theta. Not inverse means reciprocal of tan theta. Reciprocal of tan theta. And therefore S can be written as dVg by d of log 10 ID, and it can be converted to Neperian log, and ultimately we can get an expression which looks like this. S is equal to log 10, and that is derived here in terms of a parameter which I have already told, A, and CD. CD and CI. CD is the dynamic capacitance or depletion layer capacitance of the surface, and CI is the insulator capacitance. So we get an expression for S like this. And if A is very large, of course this is a simplification. If A, this term can be neglected with compared to unity, and the equation is further simplified to this form, which I derived in the last class. So up to this we derived in the last class. We were able to derive an expression for the subthreshold slope, which I told is a very, very important parameter, device parameter of a MOSFET. Now let me repeat, let me once again write here S, which is in the approximate form, is ln 10 multiplied by VTI. This is thermal voltage, please. 1 plus CD by CI. CD is the dynamic capacitance or the depletion layer capacitance. And if you see the general expression, this here we assumed A is very large, and A was defined as like this, root over 2 epsilon S epsilon I di divided by LD. And if you remember LD, the Debye length is KT So knowing this expression for A and LD, you are now able to compute the value of S as functions of any parameter, either Na or temperature or insulator layer thickness, and so on and so forth. Okay. However, if I assume that A is very large, then the equation gets simplified to this, where we know CD is related to the depletion layer thickness, and depletion layer thickness is inversely related to the square root of Na and directly related to the square root of I psi S. So we know how we can calculate S for the different values of this. In fact, if you compute the value of S using those equations, we get interesting results. So this is S in millivolt per decade, subthreshold slope. 60 millivolt, 80 millivolt, 100, 120, 140, and this is the parameter A, 0. The parameter A, you know that it is dimensionless. Epsilon S by epsilon I, di by LD is dimensionless. We get interesting results, something like this for typical calculations. Sorry, this I have done little bit. It should be like this actually. This is for different values of VBS. So one important thing to note that the subthreshold slope can be lowered, can be reduced by applying a VBS. is substrate bias, a reverse bias between the substrate and the source. Can you tell me why it is possible? Looking at this equation, for different values of VBS, ACE has been plotted against A. And it shows that as we apply a reverse bias, the subthreshold slope is lowered, which is desirable. Is it not? We need a very sharp threshold. A sharp threshold means a smaller value of S. For the same value of A, which is 10, you see that for VBS 0 volt, it may be around 100 millivolt per decade. Whereas for 5 volt, it gets reduced to about 70 millivolt per decade or 60 millivolt per decade, in that range. Can you explain why the subthreshold slope has been reduced by the substrate bias? This plainly, it is, CD, it is equal to 1 plus CD by CI. As we apply a drain bias, substrate bias, the depletion layer thickness widens, and hence CD is reduced, and therefore S will be reduced. Very straightforward. So it is an important observation that VBS, with increasing VBS, threshold voltage is increased, which is undesirable. Is it desirable? Applying a VBS, threshold voltage is increased, which is normally undesirable, whereas threshold slope, subthreshold slope is reduced. It's a very desirable feature. So remember the inverter circuit where I told that the driver does not suffer from any substrate bias or body effect, whereas the load suffers from the body effect. Threshold voltage is increased due to the body effect, and it becomes a function of the input-output swing. But in one respect it is greater because the subthreshold slope is reduced. Therefore, such load in the inverter circuit can better function at a lower threshold voltage, at a lower driving voltage. Let us now discuss a little bit about the mobility behavior. This is very important. So this is our inversion layer. When you apply a gate bias, which is more than threshold voltage, a strong inversion layer is formed. If drain bias is 0, the inversion layer will be uniform in thickness and intensity and density. But as we apply a little drain bias here, Vd more than 0, then the inversion layer density or inversion layer charge density will gradually decrease towards the drain. In fact, at pinch off, this will be just 0. Qn at L will be just 0. Now these electrons, they move. Actually, electrons are moved which direction? In this direction. But the current flow will be in the opposite direction. This electron movement is taking place in this direction. And the movement of this electron means the velocity of these electrons is a function of this is my x and this is my y. This is the origin. That is the usual assumption. Along y is a channel perpendicular to the surface is x. That means depth-wise direction is x. So Vn, the velocity of electrons along the channel, which is more or less our current, is determined by that. Id is determined by the electron movement along the channel, along y. So Vn is a function of electric field along the y direction, y component of electric field. Should it also depend on the x component? Because now these electrons, they experience electric field not only in the y direction because of the channel potential variation, ohmic drop in the channel, but also a normal component of electric field induced by the gate voltage. The electrons in the inversion layer experience two electric fields, one along y, along the channel, which is directly responsible for their movement along y, whereas they also experience an electric field perpendicular to the channel, and that is induced by the gate voltage. So do you think that Vn should be a function of Ey only, or Ey and Ex both? Ex both, because it is physically expected that when a crowd is moving, if there is a perpendicular force, a force perpendicular to the flow of the crowd movement will be affected. Similarly, in Hall effect, if you remember, Hall effect, with application of a magnetic field, deflects the carriers perpendicular to the flow, and that results into a resistance called magnetoresistance effect. Similar thing is going to happen here. In fact, that is this. Normally, when you consider the velocity of a carrier, we never consider any normal component of velocity, electric field. We assume that the velocity is proportional to, normally what we do, we assume that Vn is proportional to Ui, and Vn therefore is something like mu n into Ui, where mu n is called the low field mobility. Mu n is called the low field mobility. But in this case, what is going to happen, that this mu n is also a function of Ex. This mu n, the so-called low field mobility, is also a function of the electric field perpendicular to the surface, and it can be simplistically modeled as something like mu n0 divided by 1 plus alpha mu n half. Similarly, if it is for holes, this is for electrons, for a P MOSFET for example, this can be approximated as where mu n naught and mu p naught are the values for which Ex is equal to 0. That means when there is no transverse electric field. Mu n0 and mu p0 corresponding carrier mobilities for electrons and holes. Whatever this is for NMOS, this is for PMOS, applicable for PMOS. So these are the two mobilities without any transverse field effect, whereas alpha mu n and alpha mu p are two parameters whose values are typically like this: 1.54 into 10 to the power minus 5 centimeter per volt, assuming that electric field is expressed in volt per centimeter, whereas alpha mu p is equal to 5.35 from a typical measurement in published literature. Okay, so you'll see it's a very interesting thing that the velocity of the electrons is proportional, usually it is proportional to the lateral or longitudinal component of electric field. Longitudinal, in this case it is the, I should say, the along the channel or longitudinal component, whereas mu n itself is not a constant, but it depends on the normal component of electric field. The lower is the value of mu n, higher is the value of the normal. That is reflected through this equation. People have done a lot of work. For example, typical experimental data shows that mobility versus transverse electric field curve may be like this. This is a typical curve like this. Sorry. This is for increasing the value of temperature. This may be for 25 degrees centigrade, whereas this curve may be for 100 degrees. The intermediate one is for 100 degrees centigrade. So the transverse electric field causes the reduction of the mobility. This is actually mu n naught or mu p naught, whatever you go. Sorry, this is the value of mu n, whatever I have shown earlier, is given by this. But another interesting thing is whatever is observed is this. Now, if velocity is plotted against Ey, velocity is plotted against Ey. Typical things may be 10 to the power 6 centimeter per second and 10 to the power 7 centimeter second, and is a log scale. Maybe like this, 2, 4, 6, and like this. And this is again a log scale like this. This is a very important effect. In fact, the velocity, which is proportional to the electric field, that happens only at low fields, and that proportionally constant is mu n. But with increasing value of Ui, you know there is a velocity saturation. Typical hot carrier effect. For the bulk material, when there is no question of a normal component of electric field, the velocity gradually saturates. You even remember for the case of silicon, the saturation starts somewhere around 10 to the power 4, about 10 kilovolt per centimeter. Then it gradually saturates about 20, 30, 40 kilovolt per centimeter. Whereas here you see that the same thing happens, in fact saturation velocity, but for a normal component of electric field, the mobility velocity is a function of not only Ui, but also Ax. And therefore, there is a need for modeling the mobility of electrons in the inversion layer very accurately if I want to get an accurate expression for ID. The drain current expression in a MOSFET requires an accurate mobility model, and this mobility model is different from the normal mobility model because now the carriers experience not only a field along the direction of their motion but also perpendicular to the direction of the motion. And for that, lot of work has been done, but simplistically let me tell you, we shall discuss it while discussing the MOS models after 2-3 classes. But one thing, please note that ID sat can be replaced now as WCI into VG minus VT into saturation velocity. This saturation velocity is now a function of the transverse electric field, and GM is equal to WCI into Vs. So what I just wanted to mean is that in the case of MOSFETs, the mobility models are more complicated than the mobility models which are normally used in the case of BJT. Because now the surface carriers, the carriers in the inversion layer, they are sensitively dependent. Their motion is sensitively governed not only by the lateral field, which becomes very high at the pinch off region, but also on the transverse field. A small applied gate bias, therefore, as you change the gate bias, the change of current is not only due to the surface potential variation, but also due to the potential variation, but also due to the mobility variation. As you change the gate bias, the change in ID is not only due to the surface potential variation, mean through MOS effect you are changing the concentration of Ni, the inversion carrier density, and that is controlled by Vg. But it is not only that, it is not only the Ni, but mu, the carrier mobility, that is also determined by the gate potential. So there is a double action. The ID is influenced by the gate voltage, not only by the sensitivity on psi s and hence Ni, but also on the sensitivity to the mobility variation. So with that, I will close the talk today. Thank you.